We're going to spend the next hour here. I'm going to, well, first we'll demo this game, leveraging vector databases and LLMs. We'll talk a little bit about that. After you see the game, I'll talk to you a little bit about the sort of architecture that I put in. Also, maybe show you how ridiculously unintelligent these sort of LLMs are, which is why we did things a certain way. And then you can definitely ask questions. The source code is not open source for this, but I can share some code during this session for things I think if it's important. And then we've got the AI training repo that kind of walks you through how to do these different things. And there's a whole video series that goes through the AI training repo. And after this, we're going to record some more stuff for you there. So I thought it would be a fun introduction to some of this stuff. Been working on this particular thing on and off since the summer. I mean, not full time. I have other things to do, but finally got it in a place that I think is pretty cool. Okay, so I'm going to switch over here. And if you want to follow along a little bit there, he's going to tell a Connect. That's funny. He's going to tell a joke about Connect4, but it didn't line up. That was good, Kevin. Thanks. That's a dad joke, and Kevin's far away from being a dad. But I'm going to put that one in my database. Okay, so we're going to be fine. All right, I'm going to go to ardanlabs.ai, Ardan Labs, and the cool thing is in a week or two, we're going to have some more demos for you to play with in here too. So Kevin and Eric and I are trying to find time every week to add some new stuff to this website. But the first thing that we're letting people play with now is the Connect4. So if you want to go to ardanlabs.ai, you can do that. And you could scroll up a little bit and you'll see demo our game. Now, we've never had more than maybe 2 people playing at the same time. This is all running in Cloud Run. Google's cloud provider there. We're using some Google storage for stuff. I'll explain why in a little bit. We also have a hosted MongoDB for vector stuff. We'll talk about that. And we're using Prediction Guard to access models. Again, I'm going to get into all sort of the architecture, what we're doing. But let's just demo the game a little bit here. Now, you can log in with Google, or you can log in with an email address. One thing here is you can't use the plus anymore on your email addresses, or you'd get unlimited play. Because accessing these LLMs cost money, we have to limit people to a few games. Now, if you really want to play more, you can just send me an email, bill@ardanlabs.com, and I'll up your count. That's not a problem. You do see Bill plus AI in there because I allowed that up until Eric said, Bill, what are you doing? You can't let plus AIs because then you have unlimited email addresses. So you can log in with Google or log in, but you got to get a code first if you don't want to use the Google login. And then that code is good forever, or at least to the number of games that you have. So I'm just going to log in with the account that I've been playing with. This front end has been written in JavaScript using Phaser for some of the graphical stuff. It's talking to a Go service that we wrote that we'll talk about from architecture. And then again, it's talking to Prediction Guard in terms of accessing models and things like that. You can see here that I've gotten to choose from. I won't play an entire game, but if you did log in, you can play a game. But you can see now that the users made their move. There's a call to the server. We'll talk about that. Now an LLM made a move. And you have the debugging sort of information that we're getting out of the LLM here at the bottom. And you can see the thing that I'm always looking at is the choice number, the options that the LLM had to choose from, the choice it made, and the score 100%. We'll talk about what that score 100% means. And then we also asked the LLM to make a sarcastic response, which it did there. And so as you're playing this game, as we'll learn, the AI system is learning from you. So if you play very poorly, it's going to learn how to play poorly. If you play really well, which is what I hope, then it will learn how to play well. And every once in a while, somebody sends me a screenshot this with the board and says, the LLM should have made this move, in which case we can sort of fix the training data. And I'll show you some of the training data that we create. I'm going to show you all of this, but I'm just playing a little bit here so you've got something visual in your head to kind of look at. So these are API calls that are going back and forth from the browser to a Ghost service, and the user's making their turn, and then an LLM is making its turn based on some training data. So I'm not going to play any more here, but I will show you sort of an architecture of what we're doing, and then I'll show you some more of the details. And I'll definitely leave time for questions. Now, again, because we're playing an LLM here, this isn't going to be as smart of a system, let's say, that has actual pure algorithms that are looking at moves ahead and things like that. We're not doing that. The real exercise for me here was to learn how to leverage LLMs and vector databases in a way of building like production level apps, but to do it in sort of a fun way. Okay, so you've sort of seen the game here. Hopefully some of you are playing it out and trying it. But let's go back at this point and now sort of talk about a high-level architecture of what's happening here so you can get a visual of what's happening sort of behind the scenes. And I'm going to go into this is a private repo for this, and what I'm going to do is add a whiteboard from my favorite plugin ever. That's not it, it's this first one, Excalidraw. And all I got to do is create a file named this, and I have a whiteboard. So let's do it. New file. There it is. Boom. Nice. Okay. So let's do a high-level sort of architecture on how this game is played, and then go into some more details here. Okay. So at the heart of this game is a service that I wrote in Go. So we've got our Go service here. And it's the Go service that browser front end that we wrote is talking to. Browser is talking to it. So that's a very traditional sort of architecture, right? Just to protect your keys and anything else to the other services that you're sort of talking about. Now, after you authenticate, you may have noticed in the browser that you got a JSON web token that's right there that gives us information about a little bit about who you are and what game you're playing as opposed to everyone else. So there's an authentication piece where you get a token, and then we essentially establish what we would call a game in the system. Nothing out of the ordinary just yet. And it's that game that is allowing you to sort of go back and forth. And the API set for this isn't even that robust. I mean, if I go and I look at the game domain here in the code, I mean, that's the entire API set that we'll be using. It's, hey, start a new game. It's the AI's turn. It's the user's turn. What is the current game state? And then if you want to hear the AI speak, we've got an audio API. So this is like everything, right? We've really sort of didn't want the UI to have any sort of game logic or anything. It just needs logic in terms of whose move it is and what the current game state is to render that screen. So it's not a very big API here. And really the big parts are the AI turn and the user turn related to this. But let's talk about the sort of the AI turn piece, because that's the fun part, right? There's a bunch of things that have to happen there. And ideally what I wanted was the LLM to be able to play against the LLM and try to give the LLM some level of intelligence about Connect4. Now that proved to be really, really hard. In fact, I can sort of prove that to you a little bit. If I switch over to my AI training repo, and I come over here to the AI training repo, what I can do is start an Ollama. Let me start an Ollama service. Now, if you've never played with this stuff before, this is a public repo. It's called AI training. It's what I've been doing some video trainings around. Ollama is a model server that lets you run some models locally. I'm running on an M2, and it's powerful enough to run some smaller local models. In fact, now that I've got Ollama running, I can do an Ollama, let me make this a little bit bigger. I can do an Ollama list, and you can see I've got a few models there, like the Llama 3.2. Now, this isn't the model that I'm necessarily using for the game, but all these models are fairly similar here. So what I'm going to do is a compose up here, and that's going to run a UI called the Open Web UI, which I use sometimes to play with some prompting here. So remember what I'm trying to do. Originally, the idea is I want to have an LLM be given some information and to make some moves on my behalf and try to teach the LLM how to play Connect4. So now that I've got Ollama running and I've got my open web, again, you can come to the AI training repo. All this stuff is available to you today. I can open up a localhost 3000, and I can play a little bit with talking to one of the models. Now, again, I'm not using Llama 3.2. I'm using models that are available on the Prediction Guard system. We'll talk more about that as well. But ideally, I want to try to get an LLM to be smart. Now, one of the first things I did over the summer when I started learning this is I asked the LLM, what are the rules for Connect4? Because if it already knew the rules, then I thought maybe I don't have to train it. And like all the models that I've played with, I've gotten back sort of responses like this, right? Where, yeah, I know how to play Connect4. That's the equipment. Here's an objective. That's how to play. And you might even say, show me an example of a Connect4 game board, right? And in many cases, I got this sort of feedback back where you can see that it has a recognition that there are rows and columns and cells, and you've got different players, like in our case, maybe red and yellow here, and they can be in different positions. And I thought, wow, this is going to be easier than I thought, because since these LLMs already know the rules and they already know what game boards look like, I thought, you know what? Maybe we don't have to do much more than ask this LLM to do something. Now, you can see here that X and 0 are kind of in the middle of the board instead of the bottom of the board. But some of the first things that I tried to do were things like this, right? So given a board that looks like this, let's say, where it's 0, X, actually, she's a 0. 0, I don't even know. Let's use the exact character they're using there. Let's say, so it's capital 0, X, 0, 0, maybe nothing here, right? So maybe based on that, what is the next move X should make, right? And I went down this path for a few days, thinking that the LLM could potentially do this. And I started trying to build prompts that were smarter and feed the LLM examples and do all these things. And I came to the conclusion pretty quickly that these LLMs are really good at autocomplete, but they're not the best at answering or making sort of game level decisions or even counting, right? So how many 0 pieces are on the board? I'm doing all this on the fly with you. And you can see here it said there's currently 4 O pieces, okay? And look, this is all wrong, right? And I quickly learned that this was not the approach I was going to be able to take. That these LLMs are not necessarily smart. They're really good at trying to figure out the next word, the next token that's required, and then they just appear magical. Okay, so this wasn't going to work. I couldn't just feed game boards and ask it to make decisions. This was never going to happen. So how can I get the game working with an LLM making decisions like you're seeing here, where I still wanted at the end of the day, the LLM to be making the decision. I wanted the LLM to be the thing that you were playing. How could I give the LLM enough intelligence where it can auto-complete and within the scope of the auto-complete, let me come back here, do this. So I took this sort of strategy, and it also required us to create some sort of training data related to this. So I've learned that the more specific you can be with the LLM, the better opportunity you will have to get the LLM to make a choice that is reasonable and or magical. So let's talk about what I did here. What I decided was that we needed to create in some form or another what I'm going to call boards. And these boards would represent some state of the game at any given time. And I started off by writing these boards sort of manually. So I created a terminal UI, and as I played a little bit, I would capture an image of what the board looked like. Now, if I go to Zarf game training data here, you can see what one of these boards sort of look like. And I used those green, red, and blue markers. I write this board to a file. This file is also saved now up in Google Storage, so we can play there. And I also then have a JSON document that identifies how many red markers are on that board, what potential moves the red player could make based on that board, and then what sort of feedback we would want the red player, who is the AI, to sort of make. And so the idea was the more we played, the more of these boards that we could produce. And in the early days of this game, like within the first month of this, sitting at my table in the summer, I was sort of producing these boards manually. I would produce the board here, but I would manually start identifying what I thought was the best move that the AI could make. We have close to about 9,000 boards now. Let's do, 9,063 boards now. And trust me, I didn't do that manually. I had to find a way to sort of automate this training data. We'll talk about that. But the idea now was that we generated all sorts of training data based on board configurations and what we thought the AI should do next. Now, with that training data in mind, here's those boards. This is our training data. I wanted to be able to give the LLM the correct board to make a decision about. So it has to be able, we have to identify based on where we are in the game at any given time, right? Especially if I already have this board saved, that would be the best, because then we would have an exact information to feed the LLM on what to do next. And that's where that number 100% comes in. You can see I don't have a 100% there. This now means that I don't have an exact board saved yet that looks like this. We're now sort of in uncharted territory there, because if I have an exact board, then I feel confident that the AI is going to make the best move. If I don't have an exact board, then how do we deal with that? What if that board doesn't exist? How does the AI or the LLM make a decision? Okay. Let's talk about how all of that sort of works. So what we did is we started creating all this training data, You've now seen what some of it looks like. And what we needed next was a vector database. Now, there's a lot of vector databases out there. They all essentially work the same way. We chose to use Mongo because we're just really familiar with MongoDB. I know a lot of people don't like Mongo for some reason. I like Mongo a lot. I use Postgres and Mongo when it makes sense to use one or the other. And Mongo has something called Atlas, which puts a vector database on top of it. And the vector database works great. And so what we do is when we get some new training data, when we get one of these boards, what we do is we run it through a second model that knows how to embed. And in other words, what we do is we take that training data, we take this board, this training data, we vectorize it, which means that we're producing in a vector of 1,024 basically floating point numbers. We're putting it in space. And then we store that vector in the database with all that metadata. And so every one of these boards get vectorized, placed in the Mongo database related to its metadata. And we put it in space. And I've got videos on YouTube already in the AI training series that goes into deeper detail here if you want to learn more about that. And I've got code in the AI training repo that does that. So now I've got, in this case, 9,000 of these boards that represent some specific set of red and blue and spaces and what the AI should do. And then we vectorize it and we put it in the Mongo database. So now what happens? So now it's the AI's turn. So what does the AI do at that point? Well, the AI says, okay, it's my turn. What do we want? Well, we say, what does the current game board look like? So maybe this is the current game board. Here it is, current game board. We know what that looks like already because you've been seeing it here. So we look at the current game board. There it is. We take the red and the blue and the spaces, and we also create an embedding, or we vectorize that. And then we go and we do some sort of query against the database. So now we do a vector query, basically, or sometimes it's called just a vector search. All right? So we do a vector search, and we say, hey, Mongo, do you have a board that looks like this? And if not, just give me back the most similar board that you have. Now, in this case, we know it didn't have an exact board. It says 99%. So what it did is it brought back a similar board. Now, let's take a look at what that similar board sort of looks like here. We can find it. Should be able to find it by, there it is. So this is cool, right? This is what the game board looks like. It's got red, blue, 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 red, blue, blue, blah, 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 blah. And then this was the most similar board we had in the system. We didn't have an exact match. When we have an exact match, we know that the game should play perfectly. But when we don't have an exact match, because there's, I don't know how many potential combinations there are with 42 squares that can be one of 3 positions. I think Kevin and I were looking that up one day. We got distracted, right? But we already got 9,000 of these boards. But still, even with 9,000 boards, we didn't have this one yet. But this is the most similar board. So now it gets interesting because what we're going to do is feed this information into the LLM based on the similar board. And we hope that the similar boards allow the LLM to play in a very smart way. Now, this board says that the LLM should make a move in column 4, which is what it did. And making a move in column 4 actually wasn't that bad. And that's sort of the power of vector search and similarity, where you didn't match it 100%, but we had a board that was similar enough where that move on the similar board still was a good or decent move on this particular board. But here's the cool part now, right? I told you that I was training this thing manually to begin with, but not anymore. Now, every time this blue player moves, we invert the board and pretend that red is playing. So when you're playing, you are making the AI smarter because it's following sort of your instincts in what you're doing. Now, let me make the next move here that I think is the best move to make. So I'm going to save that question for a second, but I just made this move here. Now the AI is going to make a move. Let me do something here. I'm going to go and pull down the latest boards that have now been created since we've been sort of playing. Now, somebody else, okay, all of you have been out there playing. So we got a whole bunch of new boards out there. So the chances of me finding the board that I created for my game right now are going to be slim to none. But because all of you have been playing, we've got about 50 new boards that have been sort of generated. These are all new boards. That might be even close to what we did somewhere around there. Now, one thing that I do with these board names is it's a hash. So I take this data and I hash it. That way I know that each file is unique, and we could do a quick lookup for a board that looks like this. So these are all boards that you've been playing. And you can even see here on this board, we taught the AI how to win because the blue probably won. If one of you out there were playing and won against this board, where you dropped your last marker here in column 1, this is an inversion of the board that you were playing with, and you just taught the AI how to win on a red side. Here's a block. Here's the same board inverted, right? And this is where you won. Whoever this was playing this game, they ended up winning. But I used that to also teach the AI how to block. That's if it was their turn on this board. And this is why we're generating so many boards now. Because though I had to start manually, now, based on how you're playing, now, if you play poorly, like Kevin likes to do, then what happens is the AI starts to play poorly, and then I've got to go in and fix these boards. I have a mechanic where I can go in and fix these boards and republish them. So as all of you have been playing, you've actually been teaching the AI how to play even better. Here are boards that already existed where somebody played 5. Here, somebody played 4, so now 4 is an option. And it's 4.5 billion possible board states. So, but even though there's 4.5 billion possible board states, how many of them are actually reasonable to ever be produced when trying to win Connect4, right? So I think there'll be less than that. But you can get a sense here of how we're creating specific training data to feed the LLM. Okay, brilliant. Now, great, Bill. You've got a board here, but we still need the LLM to make some sort of decision on how to do that. So this is where now what we're going to do is the following. So we've got a game. The game has the current board, like I said. So what we're going to do then is we do that vector search. Let me do this here. I'll put vector search here. I got all your questions. I'm going to answer my problem, I promise. So we do our vector search. Our vector search then pulls a board. We get a board. And then what do we have to do? Once we get a board back from the vector search, the next thing is to talk to the LLM. And I really want the LLM to make a decision. This isn't me about building smart algorithms that can do that. This was all about the LLM making the decision. Now, I already showed you using the llama that in and of itself, it isn't that smart. But with this training data, now it can feel smart, okay? So let's take a look at how we talk to the sort of the LLM now. I've never tried this prompt with 3.2. It might be fun to try it, but let's do that. So I'm going to have these different prompts, and the prompt that we're going to be using is this one called prompt pick. And I'm going to take it out of this red. I'm going to put it into a larger space that I can sort of hack on here. Let me bring it here. See if I can make it bigger. Okay. So this is the prompt that I give the LLM. I tell it, you could read it, right? Use the following piece of information, provide an answer. The user's played in game of Connect board. And then there's some things that I fill in, right? Please respond with a single column number from this list. So let me bring up the training data again, and let's see if I can copy this somehow. Let's find a good one. Here, 2.5. So from this list, okay, 2.5. So I'm going to drop that in, 2.5, there it is. Choose the first number in the list. If the score is 100%, let's say that the score is 100%. That's what we got back from the vector search. And then here's the current state of the game board. Now, I don't give the LLM this. What I do give it is sort of text of X's, zeros, and let's take a look at that code. Because off the top of my head, I don't remember. But I don't give it the little, oh, there it is right here. So dots, Y's, and R's. That's what I sort of do. With then the cells underneath. So we could play with this, right? Let me do it this way. That way I can hack on this, and we'll put this code back. But so essentially, I'm kind of curious how Llama does this. So if I do this, these would be dots. And the blues, I turn to Y for yellow, just because all of these LLMs kind of know yellow, not blue. I should have used yellow in the beginning, but I didn't. So that would be that. And then this would be that. So I'm going to take this. I'm going to put it here. So this is the prompt that I would send now to the LLM. You can see how specific it is. I'm giving it specific information, like I want you to choose a number from this list. Here's the score. This is what I think the current state of the game board is. And then the question is, which column from the list should the red player choose? And it sounds like, it feels like it's following instructions, but it's really not. It's just leveraging the magic of autocomplete to sort of do the right thing. Now, like I said, I've never tried to run this in a Llama 3.1. That's not the model I'm using, but we're going to run it anyway because I'm kind of curious. So this would be the same thing as asking the model to choose between now 2 and 5, and hopefully it follows those instructions. Now, it did give me a JSON document. It chose 5, and it gave me a reason, and the reasons are usually pretty bad. Potentially create a row with 4 pieces, take it, right? So we know the reasons are bad. Like that's what it thinks, but, and you see that also in the UI that we're playing with. I try to show you the reason, right? And if you read these reasons, you can see they're like way off. But look, here it is, the Llama 3.2 model was able to do what I asked it to do. It created a JSON document. It did pick 2 or 5. And that's what I needed it to do. So I just made the LLM look magically smart. But what I did is I gave it a very tiny instruction with a set of sort of data where it could almost not fail in providing the autocomplete. And that's sort of how you've got to work on this. You got to get these prompts to a point and ask the LLM to do one thing and one thing only. The moment you're asking it to do more than one tiny thing, you may lose that consistency in its response. So we just did that, right? We just ran that prompt. Sweet. The LLM came back with a JSON document with some sort of column number, all thanks to the training data that we have. And then the last piece is sort of this response. And now that response is based on, in the training data, whether we're going to block, whether we're going to win, whether it's a normal move. And then we'll talk to the LLM again to sort of give us that response, right? This was the LLM being smart, was choosing. But it was choosing from a very specific sort of data set. Okay, and then once we've got the column that we're choosing and the response, then we can send it back as part of the game state, apply that column, that checker to the right column, and then all this sort of magic happens, all right? All this sort of magic happens. And so we're blue, now red. Let's look at what sort of happens here. Okay, it picked that 100%, so it found the right board, MNKX, let's sort of find that here. Now, the reason I don't have it locally is because this board was just produced on the fly to make this move. So, and I just lost, so I'm gonna have to probably fix some training data here. But we do have the Go code check to see if it's going to win or lose. And in this case, if it identifies that, it will produce a board on the fly because we still want the LLM, we still want this process to work the way it does. I don't ever want a selection to be done outside of the LLM, but at the same time, I still want to be able to produce something on the fly so it plays better. In fact, you can see the MNKX board just came down. There it is. And so we just produced this board with the win. We vectorized it, we put it in the database, and then we asked the LLM to choose. And so there is this small sort of spot in here where we're trying to figure out, I would call it win-lose. And the idea is to train the game before we go through this process. That way, at least the LLM is still playing, but we try to give it some training up front based on the current board and what's happening. And again, it allows the LLM to be sort of magical in terms of that you're really playing it. But I think at the end of the day, what you're really seeing is you're not really playing against the LLM, you're playing against the data that we've been able to produce and asking the LLM to sort of auto-complete the best answer. That's on the game side. If you want to look at a prompt related to the snide remark that you get back, this would be what the prompt would look like in order to get a response. And I've played with this prompt quite a bit. I'm going to put it also in our text editor here. So here I'm giving, in fact, I spelled formulate wrong, didn't I? That's funny. Maybe fix that. So here I'll fix it later, because now, okay. Not great speller, but we'll fix that. So here's a prompt where I'm trying to get the LLM to give me a unique response that's sort of witty. In fact, I got this word too that's wrong. And if I don't do it now, I'm not going to do it. That's the one I fixed, right? Sarcastic response. Wait. Prompt pick. If I don't do it now, sarcastic, that's it. And it still worked, even though I had some spelling mistakes there, right? So here's examples of witty or sarcastic response. Should have been responses, shouldn't it? Let's do that. I'm going to do this again. I know I'm killing you watching this, but better. If I don't do it now, it's not going to happen. Examples of that, and I'm giving it examples. And then I'm giving it some game information just so it also feels real, right? So when you come back here and you read the AI message, and I'm using a different model for the AI messaging as relates to the game column selection, because different models are better at doing different things. So the model that I'm using for this is really good at taking instructions a little bit better, and the autocomplete there is a little more consistent. But the model that I'm using for these messages is a little bit more whimsical. It's a little bit more random, and there's ways of telling it how random to be. And so different models excel at different things, and you'll want to use different models for different things. So these are two different models that I'm sort of using. But you could see that if you read the AI message, the couple sentences, that it is taking note from these examples, and it is leveraging some of this data that I drop in there. And I'm doing that to also make it feel like it knows what's going on. It doesn't know anything, right? I'm feeding it as much specific information related to that board to make that feel like it's really playing. What you're really playing against is the board data and the vector search. Because if the vector search is bad, then the game is going to be bad. And the better the vector search is when we don't have an exact board, then the better the AI will play in those situations where it doesn't have the training data yet. And that, to me, is the real sort of meat of sort of what we're doing here, right? And learning how to manipulate the LLMs with the right model and leveraging vector search and producing the right data to get the LLMs and everybody to do what they want. I spend most of the time trying to think about what is the right data related to the right prompt for this particular model that we're talking to. And don't assume all models are going to behave the same way. We're seeing that this Llama 3 is behaving pretty well. And it might be a model that I could use for both chat and selection, but you really got to spend time playing with different models and seeing which one's being most consistent. But if your data isn't really specific, what you're asking it to do really isn't specific, there isn't going to be any consistency or guarantee across the lifetime of that app. Now, I did have some questions here that I saw here. What handles the determination of how close it is percent-wise? So that's all vector search stuff. There is an algorithm called cosine similarity. And with cosine similarity, that's what it's doing. I recommend you go back into YouTube and look at the AI training videos. There's one there where I specifically go through, right from the beginning, I go through vector search and vector cosine similarity, and you could see sort of how that works. Now, my data set is really small, and so it makes it a challenge when this is your data that you're vectorizing to get the best similarity. The larger the data set, I think the more accurate that similarity will be. So that's been a problem. But as I have generated more and more boards, the similarity's gotten better and better. So on this particular project, the more training data I have, the better that vector search is going to be. Do duplicate boards that are the same slow it down? No, not at all, because that's why I'm using the hash here, because this hash, which is the name of the file, sort of represents that data, right? I'm using the SHA-256 hash. So by hashing that, I already know if that board exists in the system, in which case now, instead of creating a new board, what I might be doing is adding new moves to a board. So these are new boards. There's nothing similar there. These are all new boards. But in some cases, a board might already exist. And by doing the SHA, then I know exactly what I'm looking for. Here's an update. It's a modify. Here's a modify. So, sorry, let's come here, modify. So here's a case where we already had the board. The last time we saw this board, blue played 7. This time, blue played 6. And so none of that slows it down, all because I'm hashing the data, and that now, there's no like search for it. It's here's what the board, hash it. Does it already exist in the database? Does it already exist sort of on disk and in storage? And so there's no slowdown there at all. What is this about? I feel like I've been missing out. And Eric answered that. Okay, sweet. So this is that game out there, and this is sort of the general architecture here. I'm doing that there. And we're essentially now in this loop. And then when blue plays, what we're basically doing is also trying to teach the AI. So when the AI plays or the blue plays, there's things in there looking at the board, looking for win and losses, vectorizing data on the fly, getting that data into the database. And then we've got this sort of vector search loop. And the game feels very much like you're playing against the LLM, even though really, I think at the end of the day, you're playing against a vector database, right? Where we're asking the LLM to make the final choice. There are times where there's 4 or 5 different columns to choose, and it will choose that randomly. So I could argue that the LLM at the end of the day is making the final decision, but depending on how much game data you have and how good that vector search is really going to determine the quality of the gameplay from the AI. Now, I did all this to learn how LLMs and vector databases and stuff work, and anything that you're going to be building that is going to be sort of AI related will be leveraging this same sort of technologies. It's all a matter of when you're embedding stuff, when you're pulling it down, when you're searching for it, how you're then taking that data, incorporating it into a prompt, getting the LLM to do your bidding. It's all really all the same stuff. It just could be different order, different data, different things, depending on what you're trying to accomplish here. So this is it, man. This is the game. We even found some spelling mistakes in the prompt, which I'm going to test before I push that, because maybe it starts to behave differently now because we sort of changed some prompts around. Like when I start playing with prompts, I'm using Olama or whatever system I'm using related to the models, and we're constantly making sure that our responses are correct, and then we can tweak. You'll spend a lot of time tweaking that prompt, and once you get it working for the data that you have, it just feels good, and then you can get back to a lot of the traditional development that you're used to doing. Okay, that's all I'm going to share here. Got some code I can update. Hopefully that was a good explanation of the Connect4 game, gave you a general idea of the strategy that I used to make the LLM smarter. And the takeaway, at least for me here, is you need the LLM to be very specific on what you want it to do. Less is more, and you want your data to be rich in that case, and you're really trying to get the LLM to auto-complete the answer that you want, like pull from this list, and it's able to do that. Really, really sort of small little tasks. Sometimes you might have to call the LLM twice in order to really get what you want it to do, because you can't ask it to do it all in one call. You might have to make 3 calls. Do this, then do this, then do this, small little pieces, and then eventually you start getting the responses you want. But the key is, yeah, you got it to work once, but can you get it to work again? And can you get it to work again? And can you have that consistency again? So that's how all that sort of works. And that vector search is what allows you to identify the best data to be using for these prompts when you're interacting with that LLM. And now you got a cool little game you can sort of play and you can look at. And if you do play and you feel like the LLM made a bad decision, send me that screenshot. I need that board ID and the move that it made. And it could just be because Kevin was not teaching it well enough, and we've got to autocorrect, which we'll do. So if anybody has any other questions, I mean, now is the time. Definitely check out this repo as well. This is the AI training repo. Everything that I did here in the game, there's examples of in this training repo. I'm constantly adding to it. Next year, there'll be an AI training class that I offer, just like I offer Ultimate Go and Ultimate Software Design. There'll be an Ultimate AI. It will be based on these examples, and then some bigger pair programming that we do. So everything's here. I'm adding stuff to it, and you can go a little deeper into how we built this game, and this is sort of where I learned everything here. So this is all public domain, and you can leverage that. And again, everything's written in Go. It's all Go and some JavaScript for the front end. So throw those questions. If you don't have any more questions, that's it. I hope you enjoyed that. Send me some feedback at bill@ardanlabs.com. And if there's other sort of things I didn't cover that you wanted to sort of learn and see, or things that are missing in the AI training repo, send them my way. I'll play with that stuff. I'll get it out there so you can have examples of it. And you don't have to use Python. You can do it all in Go. That's the best part about all of this. So I appreciate you hanging out with me for the last just about hour.